Hi, everyone. Welcome to the webinar today. I'm Katie Raleigh, librarian at the NOAA Central Library here in Silver Spring. And we have on the line Derek Parks from the Technology Transfer Program and Sean Waugh, who is our speaker today. Just a few housekeeping things. If you have a question at any point, please put that in the question panel. If you have something that is not a question, but a comment or an issue with the GoToWebinar, please put that in the chat panel and I will get back to you. As it is, I'm going to turn it over now to Derek to start the presentation.
Great. Thank you very much, Katie. As Katie said, this is Derek Parks, and I'm the Technology Transfer Program Manager for NOAA. And I work in the NOAA Technology Partnerships Office, which is in Silver Spring. Our office, for those of you who do not know, we are responsible for the Small Business Innovation Research Program, SBIR, also NOAA's Technology Transfer Portfolio, so all of our intellectual property and innovations that come out of NOAA, and we try to get those commercialized out of the laboratory to other users that are outside of NOAA. So that is the primary function there. And we're also responsible for our cooperative research and development agreements, or CRADAs. So as part of our upcoming initiatives in 2019, we wanted to launch a new library series that really features NOAA innovators and innovation. So this is the first of those events that we're going to be doing throughout the year, and I'm just thrilled that we have Dr. Sean Waugh with us from the National Severe Storms Laboratory. Before I turn everything over to Sean, let me just say that this series is created by our office as a way to feature innovation and creativity within NOAA, our federal employees and our Cooperative Institute employees, but also our grantees. So we're hopefully going to be getting a good broad selection from a lot of different groups that work for NOAA, with NOAA in the coming year. So we want to showcase NOAA's inventions, our innovative solutions that we're providing to stakeholders, creative partnerships, and a whole broad range of information in that area. And in that respect, we also want to make this somewhat more of an interactive session. So for those of you who have an interest or working on similar projects or having issues with your projects that might be similar to the people that we have presenting, we encourage you to ask questions, and we're going to do our best to go through those as well. So we're going to start off with Sean giving an overview of the technology, and then we're going to be doing kind of a back and forth sit on the couch roundtable type thing. And at that point, you all can certainly weigh in with your questions, and we'll have a formal question and answer after everything is done. So with that, I am going to introduce Dr. Sean Waugh. As I said, research meteorologist, National Severe Storms Laboratory, which is in the Office of Oceanic and Atmospheric Research here at NOAA. And Sean is going to tell us about what it took to launch the PASIV probe. So Sean, I'm turning it over to you.
Thanks, Derek and Katie. And no pressure going first on the inaugural event.
No.
So what I'm going to be talking about today is it's a device that we developed here at the National Severe Storms Laboratory, specifically designed to make observations of precipitation particles, particularly in severe weather environments. It doesn't have to be used in those, but that's kind of where we were headed. So the first question that one would ask is what is the problem here? What are we trying to observe, and why are we trying to observe it? And most people are familiar with a radar image. Most people have looked at, forecast models if you're looking at what the weather's going to be in a couple of days. And with a radar image, radars are really, really good about telling us, kind of in a bulk sense, the types of particles that we can expect to see in different parts of the lower atmosphere and different parts of the storm. But we need observations in those regions to be able to validate that. Most people want to know the difference between rain that's about to fall or hailstones that are about to fall. And those observations are very difficult to get. Problem being is that they're not at the ground, so you have to have something that's in the air. And your obvious choice for doing that would be, an aircraft. And there's some problems that are associated with trying to fly aircraft into severe weather. It's pretty hostile conditions. I mean, I've seen temperatures in some of our balloon flights down to as much as -70 degrees Celsius, really high winds, 100, 150 mile an hour winds. icing conditions, things that you wouldn't normally want to put a lot of your instrumentation. But these observations are really critical. Small changes in the amount of different particles, how much liquid water there is versus how much ice particles there are, what the distributions of those particle sizes look like, those have very large impacts on the types of forecasts that our forecast models come up with, depending on how they want to make assumptions with those. So we need these observations to be able to improve our understanding of weather in general, and then use that improved understanding to develop better forecast models. So if we talk about what's been done before on the next slide here, and I'm having Derek run the slides for me because we're having some internet issues at the Severe Storms Laboratory. If we talk about what's been done before, I mentioned earlier that you can make surface observations. Problem with surface observations is it's sitting still, so if the wind's blowing, you have a tendency to not sample a lot of the objects that are falling around. The wind has a tendency to blow things away from it, and it only measures things at the surface. You have no idea what's going on above it, so you can't directly compare that to remote sensing things like radar. So you put all those instruments on an aircraft and you fly an aircraft through there, but aircraft fly relatively quickly, so you're sampling very large areas on the order of 3 to 5 kilometers to make a quality observation. So you're making a lot of assumptions about how continuous the distributions of raindrops, for example, that you're sampling are over that length that you're sampling it over. They can't operate in all conditions either. You're not going to fly an aircraft through the updraft of a supercell that's got 80-mile-an-hour winds that are going straight up. Most pilots aren't willingly going to fly into that. You're not going to fly an aircraft through, baseball-sized hail. So there are limitations about where we can fly those aircraft, and those limit where our observations are. Plus, the sampling area of a lot of those instruments is very small. So we're only getting, a very, very minuscule amount of the environment actually sampled. The kind of middle ground in those are balloons. Balloons are advantageous in that you can put them in environments where you can't put a human, you can't put an aircraft, but you have no control over the balloon. Once you let it go, it's going to go where the wind carries it. So there are positives and negatives to it. And we aren't the first people to do balloon-borne observations. There are a number of groups throughout the world that have done balloon-borne observations. Most of those previous devices have slower frame rates. They do use camera-based systems, but they had to telemeter a lot of their data back because if they where they're launching it, they don't necessarily get the instrument back. So they have to send the image data that they get. They have to send those pictures of raindrops, hailstones, snowflakes, things like that over a radio link, and that limits the quality of the observation that they have. So they don't have the greatest resolution on a lot of their devices. So as far as our goal with a lot of this stuff, if we go to the next slide, we wanted to develop an instrument that can make the observations that we need safely, reliably, and we can use it in pretty much any conditions. But there's some technical challenges that we had to overcome in order to make this instrument exist. The device needs to be balloon-borne because, like we talked about, we can't put aircraft in all these different environments. The balloon can go there. But it has to be lightweight. The FAA in the United States requires that any single instrument that we have has to have a total weight below 6 pounds. And there's some other limitations that go along with that, but that's one of the key ones that we have to avoid. If we go over that, start getting into other regulations, things of that nature, and it makes it very difficult to operate in the types of conditions that we want. So we have to stay under 6 pounds. But it also has to be strong enough that it can survive being in these conditions. I mean, we're intentionally putting it in some really hostile territory. So there's a balancing act that has to go on there. But we wanted a high resolution device. We wanted something that we could get very, very detailed pictures of raindrops, snowflakes, hailstones, whatever happens to be in the environment there. So we want something, now with 4K resolution or higher. If you want to give me a camera that shoots better than 4K, I'm okay with that. We need a certain frame rate because we need to know how much our sample volume is. We need to know what the spacing is between those samples so that we understand how much of the environment that we're actually sampling whenever we make these observations. And the biggest issue that we had is we need something called a global shutter, and that has to do with how the camera actually takes the image. Rolling shutter cameras have a tendency to expose the frame kind of in a sweeping motion, and what happens with objects that are moving is that they tend to blur across the image. And if you're watching a movie, you'd never notice. Your eye would kind of fill in the details for you, and you would just see, you know, a motion picture. But when you start freezing and looking at single images, you start to see this blurring effect. So we needed something that takes the entire frame all at once, and that's a global shutter. But those cameras are very difficult to find. So what did we come up with? The next slide shows us our kind of ultimate design. And this isn't the first iteration of this, but this is the most recent one. The entire instrument body is made almost entirely out of styrofoam, which is pretty incredible that you can imagine, you know, building a structure out of styrofoam pieces and then sending it into a supercell that has 100-mile-an-hour winds and hail and rain and lightning, and it survives. And it survives repeatedly. The total weight is right at that 6-pound limit, so we are within the FAA requirements. The biggest difference between this device and a lot of its predecessors is that we have to collect this instrument back to get the data. We did not want to stream the data back to the ground. Trying to stream 4K imagery at 10 frames a second from 60,000 feet through a thunderstorm is a very difficult challenge. So we have to recover the instrument. We have some devices on there that allow us to do that with GPS trackers. And we have a very high success rate of getting these things back, which is a whole other process in of itself. But the camera that we're using is it's a pretty small camera. It's made by a company called Zimia. It's a machine vision camera. Most of these devices are meant for like assembly line type things. And it's capable of some very fast, very high resolution imagery. But the main point here is that it's very small, it's very lightweight, and it doesn't require much power to run. And that's another issue. We can't be flying a car battery on this thing. You know, we need it to run for a while on some pretty small battery sources. We do have a box on one end of the imager that you can see there where the objects actually fall through as it flies through the thunderstorm, and that box is lined with about 912 LEDs. So it's a very bright, glowing object that's flying through the sky on this balloon. But we need that light source to actually illuminate the particles as they go through. And the way the design works out, our resolution, if you look at the size of each physical pixel in the resulting image, we get about 0.05 millimeters per pixel, which is very fine resolution. We're going to be able to see some really small objects with these. And what we're after are precipitation particles. We're not looking at cloud particles or things of that nature. But it does require a computer to run. So NVIDIA actually makes it's similar to like an Arduino or a Raspberry Pi, but it's called the Jetson, and it's a microcomputer. It runs on a Linux operating system. So we actually fly that with the device, and that's actually what drives the camera and records all of the data on the 1 terabyte hard drive that we have. And that hard drive, that 1 terabyte hard drive, every time we fly this is completely filled. So we do collect a lot of data whenever we fly this. So what does it look like? You know, what are the results that we're getting? So what you're seeing on this frame is kind of a comparison between what we've had before and what we've had now. That bottom image that you see in the bottom right-hand corner, that's actually an image from some of the other balloon-borne devices that have been done in the past. Those are liquid water droplets. And you can see that the resolution isn't that great. They were limited at the technology at the time. I believe that image is probably at least 15 years old, if not 20 years old. So we've come a long way with technology since then, but with the image quality that we have now, and with the detail of the high resolution that we have now, we can see very, very small objects. So in the top right corner, there's 4 figures that you see there. The top 2 are images from an older version of the camera that we had, where we used just kind of a handheld, high def. It was a 1920 by 1080p resolution video camera. And now, I mean, that was top of the line 10 years ago, whenever we first kind of started working on this kind of stuff. And you can see some details of the objects. The leftmost image in that upper left corner is actually an acrylic sphere, whereas the upper right image has some frozen ice particles that are in there. And that's from a real storm. That was actually taken inside a supercell here in central Oklahoma. But the bottom 2 images are very similar images from the new 4K camera. So what you can see is there's a lot finer detail. That high resolution image allows us to distinguish between different ice crystal types. For example, if you actually zoom in on the image, you can see, you know, needles and interlocking crystal types in the snow plume that was basically going through that image. That bottom left image of the 4 has a series of acrylic spheres, Delrin spheres, things like that. And that gives us a size comparison, so we can actually drop something through there that we know how big it is. And it allows us to check how good our processing software is doing about picking these things out and making sure it gets sized properly. But the device is reusable. You know, the camera, the computer, all this, you know, the hard drive, we don't want to just fly it once and then throw it away. The styrofoam body gets destroyed most of the time. You know, it lands in a field or in a tree or in a river. And the body itself is very easily replaceable. I mean, it's made out of styrofoam. It costs all of $2 to build the whole thing. But the equipment itself, we can actually just, you know, recharge the batteries, wipe the hard drive off, reload the hard drive, and put it in a new body and fly it again. And that's one of the major advantages of this device, is that we can actually use it again and again and again. But this allows us to capture observations of particles in environments we've never been able to sample before, and at really high resolution that we've never been able to achieve before. With this, we can get detailed observations on scales as small as 50 meters or 100 meters instead of 3 to 5 kilometers like we've been able to do with aircraft in the past. So it's provided some big jumps in our observational capability, and we're pushing the limits of where and what we can observe with this device. And that's basically it. That was kind of our goal with the device itself.
Thank you very much, Sean. So I've actually advanced to the next slide, but we will cover some of that in our discussion. That's really amazing technology. And so it raises a couple questions for me as you were going through your presentation. And one of them, just from the standpoint of curiosity from the broader picture, is how did you go about just kicking this project off and getting it to reality? Was it just you that had the idea and the drive and the creative spark behind this, or was there a whole team of folks and you really were working interactively to put the design together, get it pushed through management, things like that?
There was a team of people. When this project originally got started, I was a mere graduate student at the time. We had come up with the idea that we needed to make these observations. You know, we had this goal that we wanted to achieve, and the instrument that we needed to make the observations didn't exist. There were some predecessors to it that gave us some kind of starting points, I guess you could say. But we took what other people had done, and we took what the technology at the time allowed us to be able to do, and we kind of merged those together. And, you know, we knew we had some constraints that we had to work with. It had to be lightweight. The only way that you're going to make something this lightweight and have the rigidity that you need is to use styrofoam. What kind of shapes can you get that maximize strength but minimize surface area? You know, diamond structures are pretty strong for that type of purpose. So those sorts of questions kind of guided the group into designing the original one. The advancements that we're making now with the 4K imager is something that I really started to push after we had finished the initial design and after we started to collect data with it. And I realized how much power that this device actually had and how many different types of research that we could do with this. You know, it's not just one avenue. So I kind of sat down and I was like, you know, the camera that we have is great, but there's 4K cameras out now. Can we make this a higher resolution? Can we make it a better device? But that requires redesigning a lot of the structure and the electrical components on the inside and the circuitry and things like that. And that's been kind of my pet project for the last year or so, is trying to make that. But the original conception was a group effort here in the lab.
Now, so you were saying, what was the original camera that you were using? Did you say it was a video camera, or what did you have in there initially?
Yeah, so it was actually just like a handheld. It was a Panasonic video camera. It's something that you might go to Walmart or Best Buy or whatever and buy and just carry around. And there are advantages to that. One of the main advantages is that you don't have to do anything to it. All you have to do is put a battery and an SD card in it and turn it on, and it records the data for you, and it processes everything for you. The downside to that is that those types of cameras are doing a lot of processing to the image in real time to be able to convert it to a video file to save. So you lose a lot of the resolution. And you can see that when you start freezing the frames and looking at individual images and really zooming in and digging into objects that are only 10 or 15 pixels across. Like, you start to see some of that filtering and processing that's going on that the camera company is doing for you. And we can't undo that. The only way to undo that is to take an image that doesn't have that quality. But that's a whole another avenue of, now you have to find a machine vision camera and develop your own program to run the camera and store the data and process the data. And that requires a lot more effort, which is where we are now. But the original camera was a off-the-shelf camera. I just bought one and stuck it in there.
Okay. So now when you're talking about the new 4K camera and the software that you're writing for that, are you able to differentiate using the software the types of particles that you're looking at when you get an image, or is that something that has to still be done by a human?
So that was one of my main goals with this. There's kind of two stages to the process. One program that we have kind of goes through the image and it actually identifies objects, figures out how big they are, measures things like how spherical it is, how bright the object is, things like that. One of the biggest things that we wanted to do with this is what you just said, is be able to identify different particle types in different parts of the storm. And the reason for that is that a lot of the previous work that's been done, there's a group out of Japan that kind of pioneered the use of what I call video sondes, devices that run on a balloon that videotape particles. A flight of theirs on average has between 200 to 400 objects that they're able to sample inside of their storm. And that has to do with their sample size and their frame rate. If you have that number of objects, you can actually sit down and look at them all and count them all and size them all by hand. An average flight for us on the device that we have now with the frame rate and the sample volume that we have, I see upwards of 500,000 objects.
Wow.
I don't have the time to sit down and look at every single one of those. So, I set out to design a computer program that would actually go through that data and use some statistical things to be able to figure out what type of particle it was, decision tree type stuff. What I'm using is a random forest method, if anybody's familiar with that. And I've actually able to develop a program that with a pretty high degree of confidence can go through that 500,000 detected objects and actually sort them into different particle types. The original version, we had 4 particle types, 2 different types of ice crystals, like hailstones and graupel, which are very similar in visual characteristics, and then liquid water. With the new one, we're going to be able to go further. I want to get it down to individual crystal types. I want to be able to look at frozen raindrops versus liquid raindrops versus raindrops that are in the process of freezing or melting, things like that. We're going to be able to go a lot further, but that is all automated. I don't have that much time on my hands.
Wow. Okay. That's very cool. One other kind of a hardware question I had was, do you have weather sealing on all of this? I mean, so it does say it lands in a river or a lake. How do you protect the equipment that's in there?
If it lands in a river or a lake, I'm probably going to get the data back, but the instruments probably aren't going to work anymore.
Sure.
Electronics have a way of not liking landing in water. They do okay in the storm itself. It gets rained on, it gets hailed on, things like that, and the devices are pretty well protected. Our biggest issue is actually lightning. We've had a number of these devices not only near lightning strikes, but I've had probably 3 to 4 devices actually struck by lightning during a flight. And if you imagine, I've got a computer and a camera and some, wires and circuitry and things of that nature that are very near a large electrical discharge now. And protecting those devices from just getting completely destroyed by a lightning strike is one of our bigger challenges. I mean, even without a lightning strike, just being in a high electric field has a tendency to fry things. So protecting it from lightning is one of our big issues. We use a Faraday cage that holds a lot of the equipment with minimal openings for the camera so that the camera can see out, but all the equipment is still protected. But we do go through a lot of iterations of that nature. And we test it. We sit it on the ground and spray it with a garden hose and see if it gets wet. We put it in environments that we can control, that we can use to test if it's going to survive the conditions that we're going to put it in.
Okay. What made you decide on that particular camera as opposed to any of the others that might be out there?
So I spent a lot of time looking for different devices. That camera at the time that I was looking around was one of the only cameras that was in an affordable price range that had the size and weight and power requirements that I needed. But most importantly, that was the only one that I could find that shot 4K resolution and also had a global shutter. Mm-hmm. A lot of the other cameras had rolling shutters, which, as I talked about earlier, that leads to a lot of problems with the image quality that we have, and it makes them completely unusable. There are some fantastic cameras out there that have rolling shutter, and they will produce beautiful images of highly distorted particles. So they're not useful. And we tested a lot of them. I spent a lot of time looking at different cameras and evaluating a couple of different ones, and none of them would work for the application that we needed. And this camera was the only one that I could find that would do it.
Okay. So from the perspective of just working internally within your lab, did you have any issues, non-specific, of course, just getting this project moving forward, or any other challenges that you had to overcome to try to make the project a reality?
Not particularly. We all knew in the lab that it was recognized that this measurement that we needed was a very critical observation, and we needed to come up with a way of doing it. And we have a team here. The division of the Severe Storms Lab that I work in is called the Field Observation and Facility Support Group, FOFS. And we're tasked with doing this sort of thing. We're tasked with designing and building and maintaining equipment and instruments to make observations in a variety of field projects in different environments with different operating constraints. So to a short approximation, we're really good at it.
Yeah.
So we were tasked with kind of designing this device to make this observation. So we had a lot of support doing it. I don't think anybody ever thought that it would be easy, but I don't think anybody thought that, this was something that wasn't accomplishable. There had also been a few other people, like I mentioned, that had done this in different parts of the world to different degrees. So we knew we had something that we could kind of build off of. So it wasn't starting like completely from scratch, that we were just making up something entirely new. We were just taking what had been done and then moving in a different direction to make an observation that was better than what we were able to do before. So it wasn't completely out of left field, but we had a lot of support doing it.
Okay. So that kind of moves me towards the commercial side of things, or at least the outside of NOAA piece of the project. What types of, you've stated how the observations are different, and what you want to get down to is crystal size. How does that help on in terms of the observations that we're doing operationally right now, or observations that somebody else outside of NOAA might be interested in doing?
So there's probably a couple of different ways to answer that question. I mean, on one hand, this instrument was designed to make observations of weather. So there's that avenue where you could go down and you could ask, are there companies that would be interested in using this type of device to make observations? And the answer to that question is yes. There are a number of companies that produce what they call present weather sensors, that most of them use laser technology, where they're actually shooting a laser across an open gap, and they're measuring the size distribution of particles and how fast they're moving, at the surface. And those work, but they don't give you a physical picture of what the device is. They don't allow you to distinguish between liquid water or ice and how big, the snow is. Is it snow or is it hail? Things of that nature. So having a system like this that, you design to fit on the ground would be a huge advantage over some of the currently available systems. There are also a number of systems that are made from private companies that are flying on aircraft all across the world that make the same observations. You could take this technology and convert it into something that was flyable on an aircraft. So there are a number of applications that would be usable for just the weather community itself. You could also use this idea, you could use this technology to make observations of anything you wanted. I used it to make observations of precipitation particles. You could, just off the top of my head, you could make a underwater version of this where it was waterproof, and actually use it to observe different types of aquatic life, in different regions of lakes or rivers or oceans or whatever. So you could take that technology and kind of apply it to anything, because the idea is to physically observe something that you can't stand there and take a picture of yourself constantly. You have a device that can do that for you, and then be able to take that information back after the fact and identify objects within it. And that has an application in probably a lot of different areas.
Interesting. Okay. So one thing I wanted to see if anybody out there listening has any questions. I'm not seeing anything on our chat. Katie, have you seen anything come through yet?
Yes, we have a few questions in the question panel. The first one's from Brendan. For a payload of 6 pounds, max for FFA, what type of lift is needed to get the device through a storm and to the levels you wanted to study?
That is a great question. The balloon that we actually use two different types of balloons. One is just a simple latex balloon. The ones that we've been using recently are 1,600 gram balloons. If you're familiar at all with helium tanks, which we do use helium, you can also use hydrogen, but I'm not too fond of putting a balloon filled with a flammable gas into an electrified thunderstorm. Seems like it's going to have a negative result. But the balloon that we use takes about 2 full large tanks of helium to actually lift it off the ground. If you were to total the lift capacity of the balloon itself, we have a total lift capacity of about 12 pounds. So, 6 pound, this is a 6 pound instrument. We've got a few other small instruments on there that are, half a pound or a pound or things like that. But we've reached altitudes of 90,000, 100,000 feet before. That's well through most of the thunderstorms that we're trying to sample. They have a flight time anywhere between an hour to 2.5 hours. So getting it off the ground is definitely a challenge. The other aspect of that is that, if you imagine a 1,600 gram balloon with 12 pounds of capacity, that balloon is about 10 feet in diameter at the ground. So imagine trying to hold a 10-foot diameter ball filled with a buoyant gas in 50-mile-an-hour winds in front of a supercell that's chunking out hail outside of it, and it's raining, and you've got all these instruments attached to it. I mean, that's a process. It takes a number of people to do this. It takes 4 people just to hold the balloon down. We have a special launch tube that we fill the balloon in that actually allows us to hold the balloon down on the ground without physically holding the balloon, because it would just rip the balloon apart in some of the conditions that we've tried to launch in and succeeded. So it is a process to actually get this thing off the ground. There is another type of balloon that we use, which is a polyethylene balloon. If anybody's familiar with the Red Bull Stratus jump that happened a number of years ago, it's the same balloon that guy used, just a whole lot smaller. That balloon itself weighs about 6 pounds, so it's a little bit heavier of a balloon, takes a little bit more helium, but that balloon isn't a rigid structure, so we can actually fly that in environments where we expect there to be hail. Because if hail hits a latex balloon, it's going to pop a hole in it, the balloon's going to rip apart, and all the instruments are going to fall back down to the ground. The polyethylene balloon kind of sloughs the hail off. It's because it's not as rigid of a structure, and it's a lot harder to tear. So that balloon has a higher survival rate in some of the conditions that we fly it in.
Excellent. Katie, I'm still not saying questions, so if you would be so kind as to...
Yeah, no problem. We have a second question from Joe. Do you assign a height and location to each particle?
Yes, we are using a radiosonde, so it's a device that measures temperature, pressure, wind speed, wind direction, relative humidity, and all of that has a GPS device on it. So we get latitude, longitude, altitude, even down to the microsecond as far as timing goes. And we use that information along with the images that we're getting so that I know exactly where all of these objects are occurring inside the storm. So I can actually create a vertical profile that shows you where the different particle types are and how their size distributions change as you go vertically through the storm as the flight progresses. So we do geotag, basically, all of the observations that we take.
Great. Okay, we have a few more. One from Larry. What is the cost of the device?
So if you were to build one from scratch, the total cost of all of the instruments together would run about $5,000. But as I mentioned, and that seems kind of like sticker shock, right? Like, oh, wow, it's a $5,000 instrument that you're flying into a thunderstorm. The body that's made out of styrofoam is very inexpensive. It's styrofoam and tape and glue, a lot of tape and glue. But the body is what takes all the impact. The body is what gets destroyed. But that's made out of $2 worth of styrofoam. The instruments themselves, while they might be somewhat expensive initially, can be reused. So the cost of doing one of these flights would be very high, but the cost of doing, say, 10 or 20 of these flights, you can reuse a lot of the same instruments. So your cost over time kind of goes down because you can reuse the equipment. You just pull the data off and recharge the batteries and you're good to go. So, but a unit just from scratch would run about $5,000.
Okay, thank you. We have a few more questions. One from John Barnes. Could you describe the microcomputer? What language is used?
So the microcomputer itself runs on an Ubuntu operating system. I've actually disabled a lot of the graphical interface part of it because I don't need a desktop computer with a monitor to fly at 60,000 feet on a balloon. The device itself is very similar, like I said, to an Arduino or a Raspberry Pi. I've never worked with either one of those two, But the idea behind these types of computers is to have, a full-blown computer in a low power, low weight environment. And the Jetson device is incredibly powerful. I believe the specifications is a teraflop of computing power, and it uses 15 watts of power at full capacity. My cell phone doesn't do that. My cell phone also dies after like 2 hours of not being plugged in. So the computer is very, very powerful, but it's very small. It's very lightweight, and it takes almost no power to run. That thing will run off a set of batteries that we have that really are not that big for 12 hours. So that device actually allows us to make the observations. The camera requires a C programming language to run. So all of the software that I've developed using the tools and the control parameters that the Zimia camera company provides is all written in C to actually drive the camera, take the image, save the image, and that kind of stuff. The processing is done after the fact.
Okay, thank you. We do have one larger comment, but Sean, I'm going to forward that on to you separately.
Okay.
So, Sean, that did raise another question for me, which is, do you see advantages in having a private company manufacture something like this? I mean, it seems like you've got pretty solid language, nicely optimized battery life, good computing power, a really good image that's coming out of it, and then the Faraday cage plus the packaging is pretty easy just to build yourself in the lab. Do you think there would be any advantages to having this manufactured in larger quantities commercially?
I'm sure there would be. A lot of these devices, whenever we put these together, I'm sitting on a table with a box cutter and 4x8 sheets of styrofoam, cutting a lot of these pieces out by hand and then putting them together by hand. To put one of these things together, given the amount of time that it takes to like glue something and then I got to walk away for 6 hours for it to dry, it takes about a week to put one of these together. And I can do several of them at the same time, but that assembly process gets sped up considerably if you have a company that can assembly line a lot of these things. So there's production advantages that would be useful to having a company produce this kind of stuff. I'm sure there are improvements that can be made to the software that, the programming code that I wrote to actually run the camera. I'm sure that could be made to run faster. You could integrate other measurements into it. I mentioned, you and I have kind of talked offline that I want to put a GPS device on this unit itself rather than on a separate unit and just kind of consolidate a lot of our observations. That could be, made easier. So there are certainly improvements that could be made to this that would get away from essentially hand building all of these devices and making it more streamlined, essentially.
Excellent. So, Katie, do we have any other questions?
Not at the moment that I see.
Okay. Well, unless something else pops in, Sean, did you have anything else that you wanted to add to the discussion?
I don't think so. I've really enjoyed working on this project. It was a good thing because I used it to get my PhD when I was in school. So sort of a pet project of mine. And I always joke, I always told people that I was literally writing my PhD on a device that was made almost entirely out of styrofoam tape and glue, which is kind of terrifying. But the device has just been incredible since we started collecting observations with this. I mean, we've seen things with this device and with its predecessor, kind of the first iteration of it that we made that we've never seen before, that we've never been able to observe in a real environment before. With the newer camera, some of the test observations that I have, I was actually able to capture an image of a liquid water droplet in the process of freezing. So wow. You were actually able to see this ice core buried inside a liquid shell, and it had these kind of tendrils of ice coming off of it. And I've never seen anything like that. We're actually able to see differences in ice density with this. So if you think about like the little pellets, like grapple pellets or sleet pellets that you see sometimes that fall in winter storms, we can actually see variations in their ice density, which gives us insight into the conditions that particle grew in. What type of conditions did it come from? Things like that. And we've never been able to capture that level of detail before. the scales that we're able to observe. So it's really exciting to me because we're kind of uncharted territory. You know, we're putting a device that we've come up with in some of the most hostile conditions imaginable, and we're getting it back, and we're getting data from it. And it's just been a really exciting process.
That's fantastic.
Derek and Sean, we do have a few more questions popping up.
Great. Yeah, start talking, and more people come up with things.
Yeah.
Since we have time. So are there plans for more flights? This is from Paul Johnston.
Absolutely. The version that we have right now with the 4K imager, I have one sitting on my desk right here because it's still kind of under development. I'm still tweaking it a little bit. Once we kind of get that nailed down, we will probably do a larger kind of research project with it where we'll actually take this out and, you know, build 10 or 15 or 20 of these things and launch them into different types of storms. And I've done everything. You know, I've done severe storms. I've done just regular kind of popcorn, everyday type thunderstorms. I've done winter storms. They all have different characteristics that we need to observe. So there are plans to kind of finalize this design and then use it to do more large-scale research in the future.
Great. We have one question about if you would talk more about the random forest method process to the 500,000 observations and how good the method works, and how did you choose that method?
So I spent some time trying to figure out the best way to automatically classify all the particles because, like I mentioned earlier, I don't have enough time to sit down and go through all those objects. I didn't have the capacity to hire an army of graduate students to do it for me. So, you know, we had to come up with a way to do it automatically. And the only way to really do that is you have to start looking at the different properties of a lot of the particles that we see and where those properties have a tendency to suggest whether it's a liquid water droplet or whether it's an ice crystal and what type of ice crystal. But the issue that you have there, if you imagine all these different metrics, so think about like its size, how eccentric it is, how close to a sphere it is, how bright the object is. Because when you look at precipitation particles that fall through this device, a liquid water droplet is mostly transparent. You get these kind of bright edges on the outside edge of the drop, versus an ice crystal has a tendency to refract light in all directions, so they show up as this kind of bright white object that's entirely bright instead of just the edges. So they have different brightness characteristics. And I can look at those on a computer, print out an image or whatever. I can physically look at it and tell the difference, but the trick is telling a computer how to tell that difference. And the hardest problem is that a lot of those properties between the different classifications overlap. There's not a definite line that you can draw in any of these that says, if it's below this value, it's this object. If it's below this value, it's this object. That sort of difficulty in those overlaps leads naturally to a random forest algorithm, because a random forest algorithm doesn't require that you know ahead of time where your dividing lines are. And for those that aren't familiar with a random forest algorithm, the way it works is you essentially build a decision tree where at the top of the tree, you give it a number of observations, say size, brightness, eccentricity, and then maybe temperature. What temperature was the object at? And it takes those and it's kind of like a Plinko machine, if anybody's familiar with that, where it uses those to decide, is it this or is it this? And then once it goes down those levels, you have another set of observations that it's given, and it does it again and again and again. And each one of these observations kind of bounces down this decision tree until it gets a bend at the end where it says it's one of these different classifications. And those trees get more complicated the more classifications you want to do. If you only want to have 2 classifications, it's pretty easy. If you do 4, it's a little bit more complicated. If you did 10 different classifications, if I had 8 different types of ice crystals or a raindrop or a hailstone, those decision trees get a little bit bigger. But I had to manually classify almost 1,000 of these objects by hand, going through all of the image that we have and picking out ones and figuring out what they are and putting them into these categories. And you use that information to build this decision tree. But you don't do just one. You do like 10,000 of them. And the idea is that no one tree is necessarily going to be right, but on average, most of the trees will. They tend to converge to a particular solution. And that's where the advantage of random forest comes in, is that I don't have to know what the dividing lines are in the different observations that we have. And then you can do this a number of times very rapidly, and it gives you like a confidence vote. So out of the 10,000 trees, maybe 9,000 of them said it was a liquid water droplet. All likelihood, it's probably a liquid water droplet. And, we can test it. We can run a set case through there that I know what all those objects are and see how it falls out. And in testing that, I found that the random forest algorithm that I developed had like a 90% accuracy rate, which is pretty high. It's not going to hit everything perfectly. It actually has a tendency to struggle a little bit more in kind of the melting layer that we see, where you have a mixture of particles, because really small raindrops, like very, very small raindrops, look very similar to very small ice crystals. So it's very hard to tell the difference between those two. But we can actually see and test that. We can figure out where its strengths are and where its weaknesses are, where it's going to do good, and where we need to pay a little bit more attention to it manually, things of that nature. But the random forest algorithm works really well. And that's not the only one. There are a number of other ones, but I was familiar with that one just through college courses and some of my own experiences with things. So that's the one that I chose, but it's worked out pretty well.
So Sean, sorry, Katie, I just wanted to ask a quick follow-up on that. How is that different from an artificial intelligence approach then? Do you have any experience with that?
I've never really dealt with the artificial intelligence stuff before. There are a number of different avenues when you start asking questions like that, like, oh, I need to classify something. There are a number of different ways that you can go. AI is one of those. It's becoming more popular, I guess, but I don't have any experience working with them.
Cool. Okay.
They all work in different ways. They all have strengths and weaknesses. It's just deciding which one you want to use and which one works the best. Exploring other options, exploring other avenues of being able to do these classifications is something that I'm interested in, something that I want to do. I only had time, essentially, whenever we were doing the first one, to develop one. But going back and doing it again and using different approaches over the same data set and seeing how the classifications differ between those is something that would be really advantageous to us, to be able to figure out like which one is actually better, or are they all the same?
Interesting. Sorry, Katie, I didn't mean to stick on you.
No, that's fine. I just had a few more questions that came in. We have another question from Joe. Are you receiving FAA permission before launching into the NAS?
So we don't, and we spent a lot of time looking at the kind of the FAA handbook that outlines all of these rules. And essentially, the way the rules get interpreted is that if we are below their weight requirements, there's a weight, like there's a total payload requirement. We can't lift anything that has a total payload. All of our instruments combined can't be more than 12 pounds. We can't have a single instrument that weighs more than 6 pounds. And then we can't have a single instrument that weighs more than 4 pounds that has a certain density. The idea here behind these regulations is that the FAA doesn't want to worry about, to put it bluntly, taking down an aircraft. So they want to ensure that if it's above those limits, then they're concerned that if an aircraft were to actually hit this, that it could cause damage, it could potentially bring down the aircraft, things of that nature. So if we go over those limits, now we have to have FAA approval. We have to get, flight control clearance. We have to have beacons on it. We have to have transponders on it. Like we have to have these big bright lights on it. Like it gets very complex. And one of the other big things is that we're not allowed to fly into clouds at that point, which completely negates what we're trying to do. So we stay under those limits to ensure that we're not going to, pose a risk to any aircraft that are in the area. Not that the conditions that we fly these things in, there are any aircraft in the area. All the planes are diverting around. They don't want to fly there. That's the whole reason why we're putting it on a balloon. But we're not required to have FAA permission. We are required to stay out of like restricted airspace. I can't go next to a military base and launch one of these things. So we are required to adhere to those sorts of regulations, but for just letting it go, no, we're not required to get approval ahead of time.
Okay, we have 2 more questions. Really quickly, what size range can this device measure? And can you also explain how the 912 LEDs are arranged in the instrument?
Yeah. So the original version, we could comfortably go down to objects as small as about 0.5 millimeter. Below that, it starts to get kind of dicey about whether it's an actual object or whether it's just kind of granularity in the image. With the new version, with the 4K camera, we're going to be able to see objects down to about 1/10 of a millimeter, maybe smaller. That's something that I'm still kind of trying to push the bottom edge to see how far it will go down before I have a hard time deciding if it's a real object or not. And some of that, we kind of figure out through testing by actually flying it and seeing what types of objects we get. But right now, we'll say about 1/10 of a millimeter. What was the other part of that question?
The LED layout.
The LED layout.
The LEDs, that's right. So the LEDs in the box, Derek, if you actually want to flip back, if you still have the thing, go back to the problem solutions slide.
Yep.
Yeah. So the 3-panel image, the image that's on that right corner in the middle, what you're looking at is you're actually looking down inside kind of the viewing chamber. So that's where all the objects fall. The opening that you see kind of into the tunnel, that's the part that the camera's looking through. So the back of the box, which would be on the bottom of that image, has this black kind of cardboard looking piece, and that's to provide some contrast. We need something that has a solid black color behind so that we can actually identify objects pretty easily. The 912 LEDs are arranged on both sides and kind of around the opening that's facing into that box. And if you actually look at that image, you can see the LEDs arranged all over the place. And this was one of the big advantages that we had over the original one, is that, 10 years ago, you had to buy LEDs in kind of like single LED packets. And, I had to solder them together, and I had to put control boards on them all and heat sinks. I mean, it was a process. And now you can buy a 5-meter roll of LED strips off eBay for almost nothing. So they're much easier to work with now. And that's what's inside there is actually LED strips, and they're quad strips. So there's 4 LEDs per roll. There's 2 strips on each side, and then there's a strip around the opening. And that gives us a very distributed light source so that we don't end up with hot spots. Because if you only had, 2 or 3 or 4 LEDs in there, you get these really bright sections and then dark sections, depending on where the lights are. We wanted to avoid that. So that's why the lights are so distributed.
Great. We have one last question from John Walker, and he's saying that in his work with NOAA UAS program, they've collaborated many times with Brian Argro at the UC Boulder site, and they have developed a small fixed-wing UAS that carries a small helium tank that fills and releases balloon solids in targeted locations around severe thunderstorms to obtain atmospheric measurements in specific storm-related locations, both in and around the storms. Would something like this be of value to your application?
I know both of those guys. That device is incredible to watch. I've seen that thing fly, and the idea of being able to carry around a helium tank on board an aircraft, fill a balloon, and let it go is incredible. It's incredible to watch. Having something like that has potential applications to this. The biggest drawback is that those balloons aren't very big. They're not meant to carry things vertically through the storm. They're meant to kind of distribute, point observations around that kind of drift or, float around almost like a radio song. So if we could make this device smaller and, lighter weight that could be carried on a smaller balloon, definitely. That could be something where you could kind of seed these things out into different parts of the thunderstorms, but getting it down to that size is going to be difficult. But that's not, not to say that it's impossible. Do I think it could be done with the technology that we have right now? Not yet. But that also raises questions about, would it be possible to integrate this technology not on a balloon-borne system, but on a drone of some kind, on a quadcopter or a fixed-wing aircraft? And there are certainly some technical challenges to doing those sorts of things, but that is something that I'm interested in doing, and that is something that I'm pursuing. It's not going to be easy, but nothing fun is ever easy, right? But there would be advantages to having those types of observations on a system like that, especially because it's controllable. So you can make observations in targeted areas repeatedly, which is one of the disadvantages of the balloon-borne system, is that it just kind of goes wherever it wants to. So we have no control over where it goes.
Excellent.
Great.
So,
Thank you.
Katie, is that everything on the question side?
Yes, that are all the questions.
Fantastic. Well, Sean, from my part, I want to just thank you very, very much for sharing this with us. It's been a great discussion. I've learned a huge amount. It sounds like there's some really good interest out in the field, people listening and coming up with some great questions as well. So I'm thrilled at how this went. So thank you very much for your time and for joining us. Appreciate that.
Yeah.
And so I wanted to let everybody know that's on the phone out in NOAA land, if you are interested in participating as a presenter in this series, please do drop me a note. It's derek.parks@noaa.gov. I'm happy to hear from anybody and everybody out there to know what your innovations are, what you're working on, and hopefully get you featured in this series. And actually it's not next month, it's January. We've got somebody from the Northeast Fisheries Science Center, Diane Capreco, who has agreed to present, and she's going to be talking about probiotics for oysters. So that's going to be, she has some really interesting experiences working with the private sector and developing her technology. So with that, Katie, did you have anything to wrap up?
I do not. I just wanted to say thank everyone for joining us for the NOAA Innovator Series, and we look forward to seeing you in January.
Great. Thank you very much. Thanks, Sean, again.
Thanks guys.
All right.